In the previous 3 videos, we saw how to derive these finite difference equations, these forms of the differential equations in the SIR model that can be integrated forward in time using the forward Euler method. We did that in a spreadsheet in episode 3. Today we're going to move on from spreadsheets to some Python programming. So we have a little bit more flexibility and a little bit more power in advancing this model. So let's take a look at how to do that. We're going to use a tool that's available to everyone for free, and you don't need to install anything. This will all be done in the browser. So we're going to go to coLaboratory is what that's short for, .research.google.com. You might need to add that as an app in your Google account. And I'm going to say that I want a new notebook. So what you'll see is we get a view. This is using a Jupyter notebook, but it's an online implementation that lets us write Python code in the browser, and we have access to all the standard Python libraries without having to do any installation on our own in the computer. We just have the browser. So first of all, let's write a loop. I'm not going to claim that this is a great tutorial on writing Python code. It won't be beautiful code or the most Pythonic code, but we're going to make it as readable as we can, and we will try to make the algorithm easy to understand. We can worry about encapsulation and Pythonic code later, and I'm sure lots of people will have ideas about how to make this more modular. So let's begin just with the loop that would advance these from the ith day to the I plus first day in our algorithm. So what would that look like in Python? Well, anytime you know how many days, how many times you're going to do something, you want a loop, and the type of loop you want would be a for loop. So I'm going to say for I in range n days minus 1. And the syntax in Python to begin the loop is to type a colon. Notice when I hit return, I'm automatically indented. I have indent set for 4 spaces here. And we're going to start typing what the loop will look like. So I'm going to say s square bracket I plus 1 equals s square bracket I. So I'm presupposing here that I'm going to create a list or an array S for the susceptible population. And we're just modeling on the equations on the left here, but in the syntax of Python. So I'm using square brackets to index this structure. And minus beta, I see over here, times what? S sub I times I sub I, capital I, square bracket I, times dt. And I like to have some parentheses to help me visually and conceptually associate this product. Now let's go to the next step. We're going to say that I is advanced in the following way, modeling after this equation again. I sub I plus 1 equals I sub I. So how do I get from the ith value to the I plus first value? I do it by adding a bit. The bit I add, again modeling after this notation, we have some constant beta that we'll define above in the code, but we're going to first model just the loop step. I times I sub lowercase I minus gamma times uppercase I of I, the ith value of uppercase I, the infective population, times dt. And again, the final line in our loop step in the algorithm, I plus 1 is the subscript, And just modeling again the blue line here in the code, we're going to say equals r sub I plus gamma times capital I sub I times dt. So here we've replicated the 3 lines in the algorithm, and this is essentially the core of what the code is going to do. These are just the instructions to get from step I to step I plus 1, and all that remains is to expand this code by defining what these structures are that we put the data into, and what these constants are that relate the data at one time step to another. So let's see how to do that next. The syntax is pretty intuitive once you get used to it. The indentation and the white space matter in Python. If you've done some other coding but you haven't used Python, this matters. Let's also rename this notebook. I'm going to call it sir.ipynb, Python notebook. And this is our first step. The code is not yet executable. We need to import a few libraries. So I'm going to import matplotlib like this, .pyplot as plt. What this means is I'm importing a library called matplotlib.pyplot, which is the library for visualization, and I'm calling it plt. This is just a nickname, a shortcut to access that library, and we'll see how that works. This causes the plotting functions to behave a lot like MATLAB, if you're familiar with how to write code in MATLAB. And I'm going to import another library, the numerical Python library, which has a lot of functions that are useful for numerical modeling. NumPy is what it's called, and we'll call it as np. So anytime I want to access this, I'll just call it np, and I don't have to type numpy. That's all that's going on there. Now, the first thing I want to do is define how long I want this code to run. Now that we've defined everything, let's move on to full screen in our code. So let's begin by defining how many days we want to model. I'm going to say n days equals, let's say 100 days, so a little over 3 months. And now let's define the time step we want to use to start. I'll say that dt, the time step, is 1, and put in a comment. I use the hash to define that this is a comment. This is the time step in days. And now let's say beta. Let's define a beta value. Remember, this involves an infection rate, so I'll say that this is 1 divided by 3, a third of an infection per day, and this is just a habit I have probably from writing Fortran code before anything else, that I'm going to use explicit 1.0 divided by 3.0, and this is the infection rate. So we could be thinking about we're infecting a third of a person per day, or 1 person every 3 days. The next constant is our gamma. That's the recovery rate. And I'll say that that is 1/14, a 2-week recovery. These comments are just for the human reader of the code. And now let's define these boxes of data that we're going to put our data into. So I want to have some numerical Python arrays that I can put these data into. So think about this. I have 100 days. I want to have a box that's 100 units long and 1 unit tall. It's an array, so it's like a matrix. We have 100 units to put data into, and to define that, I'm going to say that S, my array for the susceptible population, is a numpy array using the command zeros, which initializes this to a 0 in every place before I fill it with data. And how big is it? It's n days long. So commenting this, I know that this is the susceptible population. Similarly for I can just copy and paste. It's always better to copy and paste than write more code because it will prevent us from making typographical errors. This is the infective. And similarly, R is the removed population. This zeros function allows us to create an array that's filled with zeros. For our next array, I'd like to use a different function. So I'm going to say this is numpy a range. This structure gives me an array that goes from 0 up to some value that I specify. It goes from 0 to n days. So ours will go from 0 to 100. It actually goes to n days minus 1. So it goes from 0 to 99, giving me 100 days total. And instead of from 0 to n days, I'm going to say times dt. So if I change this dt value later, that's going to update in an expected way. Now we need initial values because this loop tells me how to get from each value to the value on the following day, to get from I to I plus 1, but I need to know what the starting value is. So I need to know that S, let's start with the infective. I'll say the infective rate at the beginning of our model, I of 0, is 0.1% of the population. We can change that later, 0.001. That's the initial infective proportion, fraction of the population. And S of 0, the susceptible population, will be 1, or the whole population, minus I of the 0th day. So everyone who's not infective is susceptible. That's what that means. This is the initial susceptible. And finally, R, the removed population, at the beginning of our simulation is going to be 0. That makes sense. So the sum of these three is 1, meaning the whole population. So that is the whole code in 21 lines. We can see it all at once here. And that's not all we want to do. We also would like to visualize this. So let's expand our code. I'm going to define a figure using PLT. Remember, that is our shorthand for the matplotlib pyplot library. So I'm going to use something from the pyplot library, the figure command, and this will be figure 1. I always like to clear my figure, so I will say figure.clf, meaning clear figure, and that means if I run this code multiple times, I will get a nice clean figure to begin again. This semicolon just lets me write 2 commands on the same line. In a lot of languages, we need a semicolon to end every command, like C, for example, but in Python, that's not necessary unless I'm having multiple commands on the same line. So now let's say PLT. So again, we're using something from the pyplot library out of matplotlib, and we'll define a plot, plt.plot, and the syntax is the x value, comma, y value. So this will be t versus s, so the susceptible as a function of time. I'm going to use a red line, and I'll make the line width equal to 3. That should make it easy for you to see. And I will label this so that we can make a legend on our plot. Label equals quotation mark to give us a string, susceptible. Spelling is the hardest part. Close parentheses, and I can see that closes this parenthesis that I started with. And now I want to do the same thing to get a plot of I versus t. So it'll be plt dot plot t comma I comma, let's use, as we have in the previous videos, green for this. So G gives me green. The line width will be the same. Line width equals 3. And label will be infective. Finally, we'll have plt.plot t comma r. So we have our SI and R. And we've done red and green. We're going to stick with our same color scheme that we've been using in the whole series. This will be blue. And line width again is 3. And the label will be removed. And now, what would we like to add to this? I'd like to have a legend on my figure, so I'll say fig.legend, use the legend method on my figure. That takes a set of empty parentheses. And just to keep everything on the screen at the same time here, I'll use a semicolon and say plt.xlabel to label the axis. I don't like to have a graph without labeled axes. This will be days. And label the other axis, plt.ylabel. That'll be the fraction of population. So we will see if this is valid or if I have any errors here by going to the play button, hitting that, and it should generate a visualization. I see that I have an error here. N days is not defined. Let's check it out. Oh, I would like that to be plural. N days on line 4 there. Try it again. I have no a rage. I might have rage, but I don't have a rage. So there's a little typo. It really helps you by telling you what the errors are there. Trying it again, and we have success. So here is the model we've gotten used to. We have susceptible, infective, and removed, and modeled for 100 days. And it's pretty straightforward to execute this code. So let's see, if I want to have 100 days still, but my time step to get smaller, what do I need to change? Let's define another number, the number of points. And the number of data points, NBTS, will be the number of days divided by the time step. So if I lower my time step to 1/10 of a day, then this will be 100 divided by 1/10, or 1,000 data points. And again, it's always better to copy and paste. That saves us from making typographical errors in our code. These arrays will be n points long. They'll have n points in them. And this multiplication still gives me the correct units for that array. So having changed my time step but kept the same number of days, I can now see that I should still have 100 days, but a factor of 10 better resolution in time. And we have a complaint that this needs to be an integer, but it isn't. So let's explicitly type it. We'll take int of n days. And now that we've changed from specifying the number of days to the number of data points, I also want to update my loop. So I go from, instead of from 0 to n days minus 1, I'll say 0 to n points minus 1. And we cut off here because we only went up to 100 when we want 1,000 data points over 100 days. Since we have 10 data points per day, let's rerun that. And now I can see I have a smooth curve that looks the same. And what this should mean is if I reduce my time step by another factor of 2, 0.05, and let's keep that in view and rerun it, I should have a graph that looks the same. And I indeed do. This looks like, to my eye, the same curves. This is never the best way to judge that we have convergence in our code, that our code is looking good. So let's instead use another function. I will say print I.max, and this should print the maximum value of I. Rerun my code. And I see that the maximum proportion of the infective population is 0.456. Let's reduce the time step by a factor of 2. So instead of 0.05 days, I'll have 0.025 days, and run it again. I still have 0.456. So I see at least the first 3 digits are staying the same. Just to see that this doesn't always work, let's go to half a day, and I have 0.464. So I have difference in the second digit already at that time step. Let's lower it by a factor of 2, from 0.464 to 0.460 to lower by a factor of 2, 0.458. Let's lower to 0.05, a little more than a factor of 2. My peak infective, the top of my green curve here, is now 0.456, and lowering by a factor of 2, still 0.456. So if what I desire is 3-digit convergence, then I'm already there with a factor of 2. So if you wanted to be a little bit more conservative, we could say 0.01, hundredth of a day. Well, we're updating 100 times a day as we advance this data, and now our model is converged to 3 digits nicely with a value for the peak infective of 0.456. And that is a Python implementation in 29 lines of code for what we did on our spreadsheet, but it gives us a little bit more control, which we'll see in future episodes.